Hello. So welcome back. And we now have a talk of Evert van Nieuwenburg. He's a professor at the Niels Bohr Institute. Is it correct?
That's right. Yep.
And so he did his PhD at ETH in Zurich and then went for a postdoc at Caltech. And he will talk today about how to use like machine learning and particular reinforcement learning for quantum error correction.
That's also correct. Thank you very much for having me. I must say I'm a little jealous that I cannot be there in person. There's a bunch of logistics that I have to take care of here, but drink some extra coffee for me and enjoy the conference dinner too. So there's only me, I think, standing now between you and a free afternoon and that conference dinner. So I'm going to go ahead and jump right into it. And I want to just stress that please ask questions. Interrupt me whenever you want. I try to structure this talk in 3 different parts, which you see here: codes, stabilizer code, reinforcement learning, and strategy, evolutionary strategies. And I expect that the middle part, actually, which is going to be the stabilizer codes, will take a bit longer than the other 2. There will be small breaks in between, but don't hold your questions until the breaks if you have any. So I would want to start actually when I designed what I want to talk about with reinforcement learning, because I think it's a bit of a lighter concept than diving into stabilizer codes. And that's also a lot of fun, I think. So let's get started with the reinforcement learning. So perhaps this is a good point for me to ask who of you has experience with reinforcement learning? I can see you, so you can raise hands and then, okay, so there's a few. Great. So for those of you who have reinforcement learning experience, there will be a few, more in-depth points that I'll make. And then I think next week, I'll repeat this also next week. Florian Marquardt, I think, is going to introduce reinforcement learning in more detail. Okay, so reinforcement learning, I think, is a lot of fun to work on. It's very different in a sense from supervised learning and unsupervised learning, typically used in settings when when obtaining data is expensive. These are some of my favorite examples. Maybe you've seen them. Let me just start these movies while I'm talking. These in particular is, I think, I love this movie. It's about agents, which are the red and the blue characters that are trying to learn to play hide and seek. So the red characters get points when they can see the blue players, and the blue players need to make sure that the red players can't find them. And so you see that what they can do, they can walk around, they can grab objects and move them, and they can lock them in place. And they are not told anything except for red players get points when they see blue players, and blue players get points every second, let's say, when they're not being spotted by the red players. And they start to figure out by themselves that they can position these blocks to block the door. Then once they do that, the red players find out they can use the ramp, and then the blue players find out that they should first put the ramp in their camp. And really all of this sort of cooperation and these discoveries are driven only by this reward signal that we'll come back to later. And I think this sort of, for me, captures the idea of reinforcement learning. It's more of a trial and error. You try something, you see if it works, you get a positive reward or negative, reward or feedback. And based on that, you adapt your strategies. And that's really, at the core of all of this. And this movie on the right is the same thing, where now there is a character that needs to, learn to walk by moving its muscles. It's very funny to watch, especially this part. So all of that sort of has this idea of trying or learning from trial and error. And if you've been following that, there was a recent result also by DeepMind, where they again have this sort of game playing agents that try to figure out all types of games. If you play games, you know about King of the Hill and Capture the Flag and these things, and they made a whole playground for these agents to play in, to explore and to find and develop strategies. So that sort of was meant to serve as a bit of an introduction to this idea of reinforcement learning, where you learn by doing, by trial and error. So you don't have in advance, per se, a data set that you can do supervised learning on if you have labels, or unsupervised learning on, but instead you're trying to gather that experience as you go. And so a little simpler than these games I've shown you before in, conceptually, maybe not strategically, you've probably seen these results where AlphaGo learned to play the game of Go. And you'll recognize perhaps Pac-Man down here or Asteroids up here. These are classic Atari games. If you're into games, you know that also games like Dota 2, if you've heard of that, or StarCraft and so on, have been attempted or have good AI players. And they're all at their core some form of reinforcement learning, where you play the game. In Pac-Man, you see if you move left, you get an extra point because you eat one of the pellets, and if you move right into a ghost, you get your game over. So the next time you see that same situation, you try something else, hopefully. And I'm going on and on about this because this idea of learning from trial and error and of formulating these as games, because it turns out, as I'll show in the second part, also quantum error correction, at least on stabilizer codes that I will explain also, can be formulated as a game, okay? And so once you have that concept in your mind that reinforcement learning is good at playing games, I can formulate my physics problem as a game, then, mix and match. So what does reinforcement learning in a nutshell do? Again, you'll get more next week. And there's only one sort of major reference that everyone who works in reinforcement learning most likely knows, which is this free online book. There's a second version now by Sutton and Bartow. And anything you can think of reinforcement learning, at least for basics and also quite some advanced concepts, is likely in there. So I would highly recommend looking at that reference. So good. Reinforcement learning has an environment and an agent. Those are the two central concepts. And the environment it describes the game that we're going to play or the situation that we want to perform a tasking in, and is described by a state at some time t. For the rest of this talk, I think so. Think of t. T is discrete. It's a little hard to write like this, but just discrete time steps. The environment also defines some set of actions that I'll come back to in a second, and they can depend on the current time step. And it defines a bunch of rewards that'll become more clear in a moment. So the agent on the right-hand side here is what is going to play the game or lives in this environment, essentially. And what it can do is it can look at the environment, it can observe the state, perhaps not all of it, in which case it's often partially observable, but let's assume for now that the agent can see the whole state. You can look at the whole chessboard or Go board. And what the agent can do is it can perform actions on that environment. It can flip a switch, it can move a piece on the chessboard, it can put down a black or white stone on the Go board. And once it chooses that action from the allowed actions that are defined or that are allowed by the game, the state of the environment changes to the next state, and the environment returns a reward signal, which is a measure of how good was this action that you performed. Okay? Was it positive or negative, or did it do nothing? And the whole goal of the agent is to collect such rewards and to collect as high as a reward as possible. So the agent will have to choose its actions carefully in order for it to maximize this total reward, which is just the sum of these rewards at every time step. And there's typically some extra factor in here, some number smaller than 1, that, you know, if it's 1, then you just sum all of the rewards. If it's smaller than 1, then the longer a reward is in the future, the less you take it into account. That's called a discount factor. So that's, you know, a trade-off. That's something that you play with. It's a hyperparameter in your system. Typically, it's set close to 1 because you want to think far into the future. Okay, so that's, I think, really the essence of reinforcement learning. And we can try to formalize that a little bit more after I show you this simple tic-tac-toe example. Any questions? Good.
So I have a question because I'm not sure how the discount factor goes between long term and new term. Oh no, sorry,
So
there is a, okay, power. Okay, now I see, sorry.
That's right, yeah, great,
Yeah.
good.
Okay.
Anything else? Good.
No, I think that's it, thanks.
Yeah, sure. So here's an example, just to make it a little bit more concrete. We're just, you know, defining now an environment for the game of tic-tac-toe. You all know tic-tac-toe, I think. And the state of that game would just be, a current state would just be, you know, a picture of the board that we could translate into a bunch of 0, 1s, and 2s, 0 for empty, 1 for a circle, and 2 for a cross, for example. And then the environment also defines which actions are possible in this game. And one way of doing that would be to just have 9 possible actions that correspond to put your symbol or your token on square number 1, 2, so we could number them, right? Some square 1, square 2, square 3, and so on, up to 9. Some of these, of course, in the current state are not legal because we cannot place our cross on top of a circle and so on, but let's forget about that for now. These are in principle all the allowed actions. And the rewards would be such that if the game is not over, then there's no reward. If the game is over and, I should have said, let's assume that we're playing as cross here. If the game is over and we either have a draw or we lost, I get a negative reward. It means I did something wrong. And I get a +1 if I win. Okay? Now, for those of you who know tic-tac-toe, maybe this is not the best example because it turns out in tic-tac-toe, if both sides play optimally, you can never win, you always draw. But for the sake of illustration, I think this is one of the simplest environments that I can think of. That's really all I'm going to need for us now to define a reinforcement learning problem. And then we have to discuss what types of agents there are, how they can learn to play these games, and that's what's coming up next. All of these games, I just said that maybe it's an interesting thing for yourself to think about in the break or another time, is how would you define the environments for these games, right? So for Pac-Man, obviously the actions are move left, right, up or down, right? Just think about playing this on a keyboard. The actions are just 4 actions, and the state is just looking at the, we can either translate this to a bunch of 0s and 1s again, or maybe do something more fancy where we have, like Eliska introduced, a convolutional network looking at all of the pixels. And you lose, you have a score of -1 if you get eaten and you're game over. And for every pellet that you eat, you get a +1, for example. That would probably work. I don't know. That's interesting for you to try and think about your favorite game and how you would define an environment for that. So now that we have the environment, notice that it's completely independently defined of the agent. Now we want to think about what is it that this agent, whose purpose it is to maximize this total reward that it's going to get. How does this agent, what does this agent have to know or have to do to maximize that reward. So I think of the agent as its goal, meaning, you know, maximizing the reward, but what it has to learn, what it has to maybe, you know, figure out is what is called the policy, which says, given a state that I'm in, so I'm looking at my current state, which action should I pick? Okay, so this policy defines the strategy of the agent. And if we have a good strategy, let's say a good policy for tic-tac-toe, then I would want it to obey this. Let's say if I look at this state, given this state, and it's our turn and we're playing cross, then, you know, I would want action 6, which would be putting my cross here, to be, you know, I didn't introduce yet what this equals to 1 means, but there's a conditional probability, right? So I want that given that I'm in this state, the probability that I choose action 6 should be 1, and all the others, so actions 1 through 9, not including 6, should be 0. And the same here, I would probably want, in this scenario, action 9 to be a very high probability, because that means I block my opponent from winning. I haven't told you how I'm going to find this policy. I'm just demonstrating that this would be, I hope, the policy that an agent discovers for playing tic-tac-toe. Does that make sense? I see no objections.
There is general nodding, I see.
Sorry?
No, I mean, there is a visible nodding in the audience.
Visible, no, yeah, that's hard for me to see.
Okay, sure.
if you don't agree, just, you know, raise your hands or whatever. Good. So I know I've said this a couple of times now. I just want to, for those of you who have seen reinforcement learning, maybe if you've seen it before and you want to know a bit more details, I wanted to give you a bit more of a structure now, because I've been hand waving quite a lot. And so typically reinforcement learning problems, or this environment that I introduced, is a Markov decision process. It, you know, goes from one state to another state with some probability if you choose an action. Sometimes, just to mention, like before, you also have partially observable Markov decision processes if you cannot see the full state. But I'm going to now discuss a way of obtaining that policy by trial and error. So I'm going to play my game, which is tic-tac-toe, for example, or Pac-Man, and I start with some random policy. And now I want to find a way of, you know, given that I've played some games, how do I update my policy so that I become better and better at this game? And becoming better meaning getting a higher score. And so for that, it's often useful to introduce not the total reward, but the future reward, which I don't know where the G comes from, but it's a very typical notation, G of T. So G of T is, is, if I write out the first part of this sum, is the reward that I'm getting in the next step, plus 1, and then plus gamma r t plus 2, and so on. So it's the reward that I'm getting from this moment on, if I'm, you know, in the current state. And that allows me to introduce this value function. And let's take a moment to look at this. So I have to specify this policy here, right? So this is given a policy. I'm going to look at a given state that I'm in, S, and the value of this state, given that I follow a policy. The policy again just says these are the rules by which I'm going to pick actions, is the expectation of this future reward, okay? Given that at time t I am in this given state. And intuitively, this just means how good is it for me to be in this state? If I'm in this state, what is my expected score that I can get from here? And that's a very important property, I think, or important concept, because if you ask a chess grandmaster or a master player in Go to look at a chess board or a Go board, they can probably go, looks good for white, right? And that captures this intuition of looking at a chessboard or looking at a game and saying, this is a better state for this or that side. So that's the value function. I hope that's clear. And we can make another related function that's often called the Q function. That is said, it's very similar. It just says, how good is it to be in this state and take action A, okay? These two are clearly related. And sorry, that's hard to write like this, related. And you can formalize this much more relation between the two if you look into this Markov decision process language, okay? Good, so the reason I wanted to get to this Q function is because this Q function is going to turn out to obey some equation that we can derive in the break if you want, but it obeys an equation that guarantees that we can find an optimal solution. I'm saying this ahead of time now. It will become hopefully a bit more clear in a moment, but the reason I'm introducing it here is because of that. So important thing to say here, this is a way, it's often called Q learning because we're using this Q function, is that imagine that someone gives you this Q function, Q star here, because I'm saying this is the optimal Q function, the best Q function you can find, is that if someone gives you that Q function, you immediately have a way of choosing the best or the optimal policy, right? Because Q function says, how good is it to be in this state and take action A, which just it's a number, a value. And so I can just pick the action A for which this Q function is the largest, the highest value, right? I hope that makes sense. So if I'm in a given tic-tac-toe state and action 6 gives me expected value in the future of 5,000, and action number 4 gives me expectation value of the reward 1, then obviously if my expected reward is 5,000 for action 6 and 1 for action 4, I'm going to choose action 6. Okay, that's given a Q function how I define a policy. These are the last two things I want to show here in terms of math, but this is what I meant before. It turns out that if you go through this Markov decision process language, you will find that this Q function obeys this so-called Bellman equation. So you see here, Q on the left-hand side depends on Q on the right-hand side at the next state. It's and you can almost see, or you can actually literally see it from here, in this equation, right? Because G of t is just R of t plus 1 plus gamma times G of t plus 1, more or less, right? So you see that there's a sense of a recursion in there already. You'll see more of that, I think, next week. But given that you have this recurrent equation or self-consistent equation for Q, there's a bunch of different ways that you've learned already, I guess, during your studies of solving self-consistent equations. In reinforcement learning, there's value iteration. You can just do Monte Carlo estimation, run a whole bunch of games and update them. What is often done typically nowadays is this temporal difference learning, which I'm just writing here such that you've seen it once. And this is really, if you wanted to implement this yourself, it's like 5 lines in Python. This is how you update the current Q function. So if I write that here, so in Python you would make a Q function, let's say, that you define as a dictionary that has state and action as a key, and then the actual value as a value, right? And then initially they're all random. Then you start playing your game many times, and you can start to build expectation or estimates for this value, right? Remember that this value here was the this is just the definition of Q of G of T, right? That's just by Monte Carlo simulation. The problem though, if you do this, if you go this route, storing Q as an array or as a dictionary, is that very clearly you can see that if you wanted to do this for Go, you run out of memory immediately, right? Because all of the possible states of Go, I think it's a 19 by 19 board, and each square of that board or each vertex can either be empty, white, or black, right? So we have 3 to the 19 different states. Of course, there are symmetries, but that's still massive. So there's no way that you're going to store that in memory. And so there you have to do something a little more clever. And the little more clever thing to do here is to go to what people call deep Q learning, in which you represent this Q as a neural network. And I've seen that you've already been introduced to neural networks, and I think most of you do know them. If you need more introduction or questions, please ask or write in the Discord or in the chat. So the idea here is very simple. Now I have a network that's going to represent my Q function as input. I'm sorry, now I have text here, but as input, I take the state, which I now have to translate into numbers, right? So let's say that the circle has a value -1, and then this square has value 0 because it's empty. This one's empty. This one is a +1 because there's a cross, etc. Then that gets fed, represented to this sort of neural network, which can be many more layers, etc. And at the output, I have a value, one value for each of the possible actions. In this case, it turns out the input is the same size as the number of actions. And each action corresponds to, should I put my cross? So this action corresponds to, should I put my cross on square 1? This one, should I put it here, etc. And I would want this Q network, of course, once it's updated and trained, to be such that in this state, this action, which corresponds to action number 6, has the highest Q value, right? And then if I want to know what, the policy, what should I do in a given state? I take this state, I feed it through my network, and I take the maximum of the argmax, argument max of these outputs, and I know that it's action number 6. Does that make sense? And now updating the weights of this network, I'm sorry, now I have to go back here, is then done using such an update equation, which is more details on that next week, or if you ask me in the break. Make sense? I think I've been going on now for about half an hour. This was reinforcement learning, or all of the basics of reinforcement learning that I wanted to tell you about, with the idea of an environment and an agent that learns how to play in that environment. And the way we've discussed which agent that could be was this deep Q network. And so the next part that I want to talk about is going to be an introduction to error correcting codes in quantum physics, in particular stabiliser codes, and how that can be formulated as a game. Right? And then once we have that, then I hope that sort of the link between having that as a game and then letting loose on that a deep Q learning agent, we'll see what happens. And then after that, so the third part would be a different way of finding agents that doesn't involve the Q learning. So I think this is a good point. I think the middle part, this part is going to take a little bit longer. So maybe let's just take, a 5 or 10-minute break. What time is it? Let's do 10 minutes and then we'll come back at 12:15. So that's 8 minutes or so.
Okay.
And then you ask questions if you have any in the meantime.
So we meet again at 12:15 then.
Yeah, 12:15-ish. Go, get some water, stretch your legs, and then we'll be back here.
Okay, so now we are all back from the break. And I think Evert can start again.
Yep, good. Welcome back. Did any questions pop up in the meantime? Any raised hands?
Yes, there is one.
There is one, good.
Yeah, one question, and that is like, we heard a lot about Gaussian processes, like by Roman Krems in the last lectures. And I was wondering, like, reinforcement learning and Gaussian processes seem to kind of do a little bit the same thing at some point, like superficially. Like, what would you do are like the main differences, and when would you use what?
Good. I think, yeah, I see what you're saying. In both cases, in Gaussian processes, I think what you're referring to is that you say you get new information and you update your current belief, your current, posterior or the prior, what you have. And in reinforcement learning, you essentially, in spirit, do something similar where you play another game and you update your Q values or you update your policy. So I think in that sense, in spirit, there are similar methods. Reinforcement learning doesn't have to do anything per se with Bayesian learning. In fact, reinforcement learning can also be completely model free, so I don't have to make an assumption about the model or prior. And I think if you want to dive more into this, I would suggest looking at the idea of this Markov decision processes where you have transitions between states, right? So there are also games where you make, you do in the same state, you choose action, A, and you end up in different resulting states. And those are not deterministic, they're still Markovian. And so there you have transition probabilities, and that's an easy place, I think, where you can hook in Bayesian estimation or Bayesian processes. Reinforcement learning, I think maybe it's too much to go into sort of a whole detailed discussion of when it's useful. Typically, what reinforcement learning is good at is it works well in cases where obtaining samples is costly. So if you don't have a very large data set, right, you could also learn to play, chess by just simulating, millions of games and seeing which moves work, or billions of games and seeing which ones work or not. But that's not very feasible. So instead of that, you try to have a strategy by which you learn from the moves you're making or the games you're playing as you go. And Q learning is very helpful with that because it has all sorts of especially this Bellman optimality equation, I want to say guarantees that if you play well, if you play long enough, you will find the optimal strategy. So I think maybe that's a scenario in which reinforcement learning makes sense. If you, have a situation where obtaining samples is costly compared to making a very large data set, that helps. And I think Eliska also mentioned this, for example, in the microscope zoom and identifying flakes. That's also something that you could perhaps apply reinforcement learning to. And I think she mentioned that, or some of you asked. Does that help?
Yes, in parts, yes. But on the other side, I'm just thinking, like, you're saying like it helps when you don't have the large data set. This is like exactly the same thing that we heard about Gaussian processes, like as in the main case of
and that's what I didn't say that explicitly. That's both of those. That's exactly right. I think that's a good question. I don't know. Maybe Roman would have a better answer to this. What the computational advantages of either over the other would be. And I think here, at least, the advantage could be that we can make this reinforcement learning entirely model free. So we don't have to, we can estimate the transition probabilities in our Markov decision process as we go. you're going to tell me now that essentially that's what you're going to do also with the Bayesian update rule. Good question still. I don't think I have any deeper insights into when to use one over the other at the moment. I don't know if there's any experts in the room that can tell more about this difference or the equation or the equality between reinforcement learning and Gaussian processes. If there is, now's your chance.
Okay, but thank you very much. That's helpful.
Yeah, otherwise, I think I'd be happy to understand this more myself too. Maybe we can ask Oman in the Discord when he's awake and then see what happens. I can try and ping him about that.
Okay,
So answer, sorry, go ahead.
No, I mean, there are two more questions / comments. So, but go ahead, continue, and then I will give the mic.
No, I wasn't going to add anything particular. Please go ahead.
Yeah, I'm actually a bit confused by what you said, because for me, reinforcement learning, I kind of see it being used in situations where you have access to a lot of data, right? Because like when DeepMind uses it in games, they use it because they have these simulations and they can play these simulations as many times as they want. So for instance, when they play chess, they play, like right now they play chess 40 human lifetimes or something. And then that's why it's so great. And then the challenge in the field seems to be like to be able to be more data efficient in some sense. So this seems to be a large data regime rather than.
Oh yeah, I'm not saying it's a small data regime. I'm saying that it works. It typically works well, or you have reinforcement learning is useful if obtaining single samples or single data points is expensive. I didn't touch at all, maybe this is confusing you, I didn't touch at all upon this so-called exploration versus exploitation dilemma, where, at some point you have a strategy that you're following, which works, let's say, but you never know if maybe there's a better strategy that you can still follow, right? So at some point, instead of following what you've learned, you will have to try something else, something random, and see what happens, right? If I always play the same opening in chess, then at some point it's not going to work. So I'll have to try and explore. And the question is, how much do I explore versus how much do I exploit what I've already learned? And I'm going this direction now because I think it ties in with how cheap or how costly it is to get one other sample. If you run this reinforcement learning algorithm for long enough, you'll get many samples, obviously. So you will need typically many samples to learn. So it's not a matter of load data, it's a matter of being efficient in which points you pick, which data points do I pick. And it can be translated to physics, right? If instead of doing a full 2D raster scan, I want to know, given all of the points I've measured so far, which point should I measure next, right? And which is the best point to measure next? Which point should I measure that gives me the most information? And that may be a Gaussian process answer, right? Which point reduces my estimate the most? Or it may be a reinforcement learning problem that you formulate and say, which action should I take given all of this, given the state I'm in, which is all of the measurements I've done. And right, so there's a subtle difference there between lots of data and between asking how, given that a single measurement point costs me some computational time or experimental time, how do I optimize which ones I choose?
Right, but typically this is kind of like decided by the algorithm that you use, right? Like Q-learning or TD Lambda. Or, so these kind of like decide like what points your agent would decide to pick next. Mm-hmm. And the different tasks kind of like do these things differently. And it's still kind of like an ongoing research thing for these things to become like efficient with just a low amount of data, right? So it's kind of like in Gaussian processes, you have a very easy way of like picking the next point. In reinforcement learning, I don't see this as being very as analytically clear in some sense.
I see. Okay, I appreciate that a lot. I think that's an excellent point. You're right. So saying with Gaussian processes, it's clear what, you know, given my measurements, what my, or given my, you know, current information, what my next step should be. And you're saying reinforcement learning, you know, which that's the policy, right? Which, you know, there's many different agents that give me different policies, and there's no analytical handle on how efficient they would be. All I can say, I guess you know that, is that at least if you go the Q-learning route, you have this optimality equation from the Bellman equation. Right? So that's, and you're right, that's an essential difference between reinforcement learning approach and the Gaussian processes. Thanks for that.
I think that was the point of the comment I was trying to make. Thanks.
Yeah, thanks. That's very helpful.
And there is another comment, I think. Oh, no.
Yeah, please
another-
go ahead. Yeah.
the comment disappeared. Okay, so that's okay, but Eliska has a point.
Thank you. I just wanted to maybe add one more point to this like data discussion, because it's just not like about saying like, okay, reinforcement learning is super data intensive, but supervised learning is also data intensive, and Gaussian processes are data intensive. So what is the difference, right? Like, it's kind of also about like what kind of data you have access to, right? Because you say, I will say, I cannot do reinforcement learning there and there because it's expensive to train. And when I say that, what I mean that when you are working with this experimental training set, you have a fixed training set, and you cannot tell them, oh, never mind, just cool down the sample and get me that more points so I can iterate the algorithm, right? So maybe your fixed training set isn't enough to train the reinforcement learning. On the other hand, imagine this Go thing, like how stupid it would be to generate all the examples of all the classes and label them and have some kind of supervised way to predict the next thing. Of course, that in principle you could do that, but like you will never do that, because why would you store like 100,000 terabytes of data to do that, right? So it's much better to then do this exploratory strategy. But this thing of like data intensiveness for the training and ability actually like freely generate the next point for your training set, that's like intimately related. So it's also about if you are in charge of your training set and if you aren't, where this kind of data intensiveness comes from.
Yeah, I completely agree with that.
Okay, I think there is no more comments. Thanks a lot.
Great. Yeah, we can come back. I mean, I think that's an interesting discussion that we can come back to maybe in the next break or so. Let me start now on the middle part and then interrupt me if there's other questions. So let's park reinforcement learning for a moment, and let's go to how we can formulate error correction, quantum error correction as an environment that we can let loose reinforcement learning on. So where this is going to sit, and this is very basic for most of you, I think, I just wanted to have the context very clear, is in this bottom layers. I think most people agree that quantum error correction in some form is going to be necessary in the future, for at least for, you know, it won't hurt NISC devices like we heard yesterday from Alba. But you know, you've maybe worked at some point with Qiskit or with Circ or with some other your other favorite software that you can use to program circuits or program software. Those get, you know, either you build those circuits yourself or they get compiled into circuits, and then those there's a lot of extra layers here, but those in the end get executed on hardware and you get back, you know, averaged measurement results. And so that runs, you know, that hardware. We've also heard about those before. There's many different implementations, you know, superconducting qubits, trapped ions, topological qubits, maybe. So this is the layer now that I'm going to discuss. How do we make such qubits not hardware based, but how do we make those error corrected? How do we make stable logical qubits? And I think a good place to start, even though it's, you know, very far back, is classical bits, where this is not what is nowadays being used for classical communication. Classical communication uses so-called low density parity checks often for error correction, especially now your 5G signal, for example, coming up uses such error correction technology, but it's all in the end based on this idea of redundancy, where, for example, very simply, what I can do is this repetition code. It's called my classical bit 0. I just encode that. It's called encoding as 3 zeros, and my classical 1 is 3 ones. And then if I had this set of 4 bits and I wanted to send that to someone, let's say I wanted to send that to you, then I use that encoding. So this first 0 becomes 3, and then these become 3 and 3, and another set of 3. I put these bits in an envelope and I send them to Warsaw, and then maybe somewhere something happens, some error happens on the bus or on the truck there, and it turns out that some of these bits flip. Okay, so in that first, one flipped, and then maybe this bit flipped, and maybe this bit flipped, and then you open that envelope, and let's say they're all kept in order, and you look at those and you see, okay, I now have to look at pairs of 3, and at this first pair, the majority is 0. So that's likely a 0. This nothing happened here. Majority is 1. Here majority is 0. So this gives you a way of decoding, of looking at where the errors happened and then correcting them. So now that you flip back this bit, you flip back that bit, and this one, you get back to this, and then this was the original bit. Now you see, there's many caveats here. Of course, what happens if 2 bits flip here, then still game over. So there's better ways. Of course, you can just, make a repetition code where a 0 becomes 50 zeros, and then you're very unlikely to have any errors. But like I said, this is not the way that modern technology does that. But the problem is that as soon as we go to quantum, there's a whole bunch of issues here that we have to deal with. So let's say we do the same thing. We encode our quantum bit 0 into 3 quantum bits, and then we're storing them, or we're doing some some computation with them, where we get phase factors, computation, all kinds of things. And then if we want to look at them, did errors happen, we'll have to measure these qubits, and then inevitably measurements will cause a collapse of the wave function, and so we'll get one of those states out, but there's no way for us to know what the original state was. So that measurement is an issue, let alone that maybe there's also the problem of taking a state and copying it. We have the no cloning theorem, right? Maybe you've heard of that, probably you've heard of that. So there's all kinds of issues that we will have to overcome, and that's sort of this simple idea of repetition is not going to work. So the whole problem for quantum error correction is that we need to find a clever way of encoding bits, quantum bits, in such a way that we can still know that an error happened, but without actually destroying the state, the whole quantum state that we have, right? Without destroying superposition that these many bits may be in. I hope that's intuitively clear. So here's a way of doing that, a very simple way that only corrects bit flip errors, and that I'll introduce in a moment. So let's say here that I can prepare in my quantum computer, I can prepare initial states, and if I can prepare this initial state, oops, sorry, let's do that this way, this state, then that's what I'm going to call my 0 state, and the 1 state, I'm not writing it everywhere, but it's the same thing, but with a minus sign. Okay, I'm just postulating these now. These are my 2 so-called logical qubits, and they require 3 physical qubits, right? So my logical qubit is encoded as this particular superposition of 3 physical qubits, 3 ions or 3 superconducting circuits. Now, you can check that we introduce this Z operator, Z acting, oops, sorry, let's do that again, my fault. This Z operator acting on 0 is 0. That's just the Pauli Z operator, Pauli Z operator, and Z acting on 1 is -1, right? Spin up and spin down. That's how I define my operator. It's hard to write, sorry. This is supposed to be a 2x2 matrix with 1 and -1 on the diagonals. And you can check now that this 0 state, as well as the 1 state, you can do that yourself, that these are eigenstates of this product of two Z operators. So this is Z acting on the first qubit and Z acting on the second qubit, and then second and third qubit. And easy to check, right? And now let's say a bit flip error happens. And a bit flip error means I have an X error happening on the first qubit. So if because now we know this state, we can just see what it does. This first bit flips and the second bit flips. And now let's look at what happens if I look at what these eigenvalues of these, or the measurements of this Z1 and Z2 are. Right, so if I have Z1, Z2 acting on this bit here, maybe this is trivial, and let me just write it just to be absolutely sure we're all on the same page, 0, 1, 1. Then Z1 acting on this gives me a -1 times Z2 acting on the 0 gives me a +1. So there's an overall minus sign. So that's -1, 0, 0. And the same is going to be true here, because I have the 0 gives me a plus and this 1 gives me a minus. So I have two minus signs, so an overall -0, 1, 1. I'm leaving out then the square root of 2. So you see that now with this X happens first, I no longer get a plus value, but I get a minus eigenvalue. And the same calculation we can do for Z2, Z3, and you'll see, you hit 0, 0, which gives you plus, and you hit 1, 1 here, which gives you -1 times -1 is also a plus. So this operator still has 0 as a +1 value eigenstate. And you can repeat this exercise for yourself and see what happens if I now have an error on X2 or a bit flip on qubit 3, and you get this particular pattern of these measurements of Z1, Z2, right? So if we just solve an X1 happens, and Z1, Z2 gives -1, and Z2, Z3 gives +1, okay? You can check that for yourself. Now I'm going to speed up a little bit here, but now I'm going to just give these operators names. So Z1, Z2, I call S1, and the other one S2. And the S is going to be very suggestive. It's going to be stabiliser. And another exercise for yourself, or if you can convince yourself that all the calculations I just showed you before, I showed you to you acting on the 0 state, but they work on any superposition. So now let's say if I have this particular state in my system, in my quantum computer, and some error happens, and then all I give you, that's something that you're allowed to do now, is measure these stabilizer operators, these values. How you do that in hardware, we can also talk about, but that's possible. It has been demonstrated for very small codes. Let's assume that it works. You or your favorite experimental friend can do that, and we measure these values, and we see that stabilizer 1 has +1, stabilizer 2 has value -1. Then we can just look up that we know now that an X error happened on qubit 3. Okay, so we never destroyed our state psi, but we do know that a bit flip error happened on qubit 3. So we can now correct it by just performing that X3 on our state again to undo it. Does this make sense? I think this is the essence of stabilizer codes. I can demonstrate one more in a moment. But...
There is one question.
So, yeah, please go ahead.
Sorry, but how do you take the expectation value without measuring?
Yeah, no, you don't. But what you in the experiment, what you do is you have your state, you have the qubits of your encoding, these guys, the three. You need what is called an ancilla qubit that you couple, right? So you, very suggestive maybe, but now let's say you have these three. Are you familiar with circuit diagrams?
Yes, yes,
So
yes.
I have my, good, okay, good. These are these, oops, sorry. These are the three qubits, and these guys are this, the zero state coming in here. What you would do is you have an extra so-called ancilla qubit, let's call it A, that you do something, you know, some typically, let's say a bunch of C naughts. This is very hard to draw, sorry. C naughts that you couple to that qubit, and then you measure this ancilla qubit. And that gives you a way of getting to that expectation value without destroying the qubits. We can talk about that more afterwards if
But then
if you'd
you
like.
essentially need an ancilla qubit for every time you correct, or how does it work? Like
Yeah,
every time.
you're going to need a whole bunch of ancilla qubits. That's right, and that's also why, in for example, the surface code or Torah code I'm going to discuss, there's a ton of overhead. There's lots of overhead for ancilla qubits everywhere to perform these measurements. That's something that maybe can be optimized still in other types of codes, but yes.
Thanks.
You're right. There's a whole bunch of extra qubits that you have to have lying around to be able to do these things. Yeah, that's why I think Alba mentioned this for some of those codes. If you want to have one logical qubit, you need, let's say, 1,000 physical qubits, and a whole bunch of those are going to be actually ancillas only. So yeah. Good. So this idea of stabilizers is very powerful, and I think for me, when I saw that the first time, very profound also, because here's a simple one. I think this is one of the smallest ones that can correct both single bit flip errors, but also phase errors, meaning plus or minus signs in front of superpositions. And instead of the 2 stabilizers I just showed you, there's 4. So you should read this as, you know, as 1 is X acting on qubit 1, Z on 2, Z on 3, X on 4. So this code has 5 qubits. You need 5 qubits to encode logical state. And then here S4 is Z on 1, X on 2, X on 4, Z on 5, for example. And I define these operators. And whereas before I just postulated, right, the 0 state is this superposition and the 1 state the other. You can just do that the other way around. You can say the code space, meaning my logical states, my 0 and 1 state, is defined as all the +1 eigenstates of the stabilizers. Whatever, stabilizers, right? So I'm just repeating what I wrote down here. So the 0 is such that it has +1 eigenvalue when you acted on it with all these stabilizers, and the same is true for the 1. Of course, those have to be orthogonal. In this case, there's only 2 of those. In a moment, we'll see a different example. And then, whenever what I want to find out, did an error happen, then I measure all these stabilizers and I see if they result in +1 or -1 values. And by that pattern of +1s and -1s, I will know exactly in this particular case, for example, if an X error happened and on which of the 5 qubits, or if a Z error happened and on which of the 5 qubits. And then all of that just by measuring, you can play around with that yourself. You see what happens if I do S2 on X on 0, and you will have to, sorry, that's not legible. S2, what happens if an X happens on qubit number 3, and to get that value, you will need to commute this X operator through this S2, which is defined here, and you will see if you have a plus or minus sign. So all of that is encoded also in the commutation or anti-commutation relations. That pattern, by the way, is called the syndrome, all of the plus ones and minus ones. So an error leaves behind a pattern of minus ones, and that's called the syndrome. I went to this a bit fast, maybe. Please write questions in the chat or Discord or interrupt me. Otherwise, I'll just keep going. So I showed you just now this code, this stabilizer code with 5 qubits. Now we're going to look at many more qubits in the form of the Torah Code, which is a very famous stabilizer code introduced first by Kitaev. Let's go through it, and you'll see that it has another property, namely there's a topological property in this code that makes it very useful. So here's a representation of the Torah Code where each of the vertices is one of my qubits, one of the the physical qubits. In the actual implementation in the lab, which I think was only done for a 2x2 version of this, there's also, for each of those vertex, there's also ancilla qubits nearby. There's also ancilla qubits in the middle of those plaquettes. Let's not get into that, but we have a bunch of qubits here, but that I'm showing, and I'm only talking about the physical qubits. In real life, there's many more of these ancillas. And the important thing that I want to say here for the Torah Code for now is that it has periodic boundaries. So this qubit here is the same as that qubit there. And this one here is the same as this one down here. There's also a non-periodic version, and then it's called the surface code. That's just for you, the more you know. Here are the stabilizers for this system. So stabilizer S1, let's say, is this one, which is the product of all the Z's on the corners of this plaquette. And then we have stabilizer 2, which is here, which is a white plaquette, which it's the product of all the X operators on the corners. And so here we have, S3. So we have 16 stabilizers here. And you can turn that, in this case, into a Hamiltonian. And you say, the code, like we discussed before, the code space are all the states that are simultaneous eigenstates of all the simultaneous +1 eigenstates of all the stabilizers. And here that's the equivalent of saying it's the ground state of this Hamiltonian, right? Because if these are all +1 eigenstates and these are all +1, then I get the most negative value. So it turns out that for the toric code, that ground state space or that code space is 4-dimensional. There's a 4-fold degenerate ground state for the Torah code. In the non-periodic surface code, it's 2. So here we have 4 ground states, so not just 0, 1, but we have 0, 1, 2, and 3, and we can use that to define 2 qubits. So Torah code is 2 qubits. Okay, and so let's now see what happens if we have bit flip errors. We can have other errors, like I said before. Let's discuss bit flip errors. So if one of those bits flip, then like in what I discussed before, that's going to leave. Now I'm going to measure all of these plaquette operators again. Yeah, all of the stabilizers, all the plaquettes and the star operators. And that's going to leave behind, as promised, a unique pattern of +1s and -1 values. And in this case, that's going to be such that all the plaquettes that that are adjacent to that bit flip error will measure to -1, and otherwise they'll just be +1. So these orange dots represent the stabilizers that measure to -1. That's the syndrome. And now you can see that's property now that we're going to discuss of the Torah code. Now, if I flip another qubit here, this plaquette here now has 2 flipped bits, and the plaquette was the product of the Z operators at the corner. If I flip 2, I have 2 -1s. So this plaquette again is happy, it's satisfied, it has eigenvalue +1. And so I can start moving these endpoints around. And now you see what happens if I make this particular pattern, I close this loop of this error string, and it's a contractible loop, meaning there's loops that are contractible like this, and there's loops that go around the boundaries that are non-contractible. You know that by putting a circle on a donut. If it's a contractible loop here, you see we're now back in the code space. There's no more -1s measurements. So we're back in the ground state. But we don't know in principle if we are back in the same ground state, right? We had 4 different ones, and we started in one. The question is, are we still in the same one, or did we move to another of the ground states? And that can actually happen. And the way you move from ground state to another ground state is by forming non-contractible loops. So let's say that this initial state represents the 0, 0. Now we have errors happening, but instead of them closing into a loop, let's like contractible loop, let's close them periodically across the boundary. So like this. That non-contractible loop is interesting for yourself to see if you can try and figure that out or calculate that. But such a non-contractible loop causes us to go from one of the ground states to another one, from a 0 to a 1. In this case, in the second qubit. So even though there's no more syndrome, all of the orange dots have gone. I now performed a logical operation, which means I flipped one of my qubits. And of course, this is interesting. This is required because if we want to do calculations on these qubits, we want to be able to perform such operations, right? Introducing this loop here corresponds to performing x2, right? Which is some operation that we want to be able to do in our computer. I see that there's a question in the chat. Nico is asking, since you have 4 vertices, how do you have the state 0, 0 and not 0, 0, 0, 0? So let's go back here quickly. That's a bit too far. The code space, right? So I look at the ground state of this Hamiltonian. It is 4-fold degenerate. So I have 4 levels, and that means I can define 2 qubits, right? So I have, let's say, 0, 0, 0, 1, 1, 0, and 1, 1, right? Those are 4 states. That's a 4-dimensional ground state, and they define 2 qubits. Is that what you're asking? While you're typing, I see. So I think maybe your confusion, you're asking about vertices on these corners and so on. So those are the physical qubits, and those are not the logical qubits. So this whole set of 16, sorry, that's more than 16, but this whole set of 1, 2, 3, 4, we can count them, qubits defines just 2 physical qubits in the ground state of the stabilizers that I'm describing here. If you're not sure about what I'm saying here, other people, physical versus logical qubits, indeed. So these are the logical qubits, and the rest is physical qubits. I'm happy to discuss more about this in the Discord or in the chat after. I just want to move forward a little bit. Good. No problem. Incidentally, I want to mention one more thing here. This picture is typically said to be, representation of a code of distance 4. And there's just, there's 4 qubits. It's a 4x4. So instead of saying it's a 2D lattice of size L equals something, in quantum error correction, people typically talk about distance of codes. That goes back all the way also to classical error correcting codes. So now, hopefully it's not too far-fetched to see that we can turn this into a game, okay? Now we're going to think about this environment that we can play with a reinforcement learning agent. And the game works like this. I ask all of you to close your eyes, and then I secretly, perform or flip one of the physical qubits. Then I calculate all the stabilizer values, and and then I hide which underlying physical qubits I flipped. So all you get to see, which is also all you have access to in your, let's say, experimental surface or Torah code, is the value of all these measured stabilizer operators. And obviously you cannot see the underlying errors, because if we knew those, we wouldn't be doing all of this. So I give you this, and now the game is you get to pick qubits that you want to flip. You get to pick, for example, one move at a time. And when you flip it, you know that the corresponding syndrome on that point will move, right? So now we can, we can move more. I don't know if anyone has a suggestion, but let's say we're going here, and then we're going there, and then if I do that, I merge my two syndrome points, and now there's no more syndrome left, so the game ends. Okay. But the game ends. You thought you won, but we're not entirely done yet. Now we have to check. Now, you say, you give me this solution that you were proposing. And I say, okay, I know that this was the error that I introduced. And, this is just like a bit flip error on the boundary. That's because this qubit is the same as that qubit. And so with that original error that happened, plus what you did, we now have this non-contractible loop that we introduced. And the rules of the game are that this is a loss, okay? Winning means making a non-contractible loop. In this case, you performed a logical operation. So we're not, whichever state we started in, which is the one that we wanted to keep and to correct, now we moved out of. So that unfortunately didn't work. But you could have also proposed this correction. This is the same correction that you proposed, but I could have under the hood performed this set of 3 errors that would also have given the same syndrome endpoint. And now if we combine these, this qubit is going to be flipped twice because you included it and I included it. What we are left with is this contractible loop, and now you win. Okay. So the whole name of the game is, given a picture of those 2 or multiple orange dots, given the syndrome, you get to move them around by flipping qubits, and you will have to figure out what is the most likely set of errors you have to introduce, what is the most likely set of qubits you have to flip to get to a contractible loop, right? So this is like a maximum likelihood decoder. That's sort of what we're after. And instead of doing that with reinforcement learning, what people had been doing before quite successfully was using the so-called minimum weight perfect matching algorithm. Now I think that's one. Now there's many different algorithms, but union find is a very interesting one, just to have that on the slide for you to think about or look up. But minimum weight perfect matching is very simple to think of. I'm going to go through it a little bit faster now, but it works like this. Just by saying, let's say that the probability that a single qubit flips is P, then the probability that a length L error chain happened is just P to the L. We're assuming that all the qubits are identical. So that means that the shorter the string is, the likelier it is. So if I have a picture with a bunch of orange dots, I'm going to find the ways of matching all of the orange dots up that gives me the shortest total length. That's really all that the minimum weight perfect matching algorithm does. And this is how it performs. Let's take a moment. This is an important plot to look at. What you see here is how likely it is for a single qubit to flip. That's on the x-axis. On the y-axis, you see if I correct my error with my minimum weight perfect matching algorithm, how likely am I to end up in the correct state? How likely am I to not introduce a logical error. So for very small bit flip rates, it makes sense that, you know, you only have a few orange dots here and there, and they're probably close to each other. So I just pair them up locally, and then almost always I'm going to be correct. At very high error rates, it becomes the opposite story. But the important point is that here there is this point as a function of making my code larger and larger, where there is a transition. So that's called the threshold point. And we can discuss this plot for another whole lecture, but the essence here is that if in my lab I can make physical qubits that have an error rate below this threshold point, then, quote unquote, all I have to do to get better and better is scale my system up. I just have to add, you know, make my system larger and larger. I don't have to improve my qubits anymore. I can have faulty qubits. That's fine. My superconducting circuits have error rates of 0.08. If I just add more of them, I'm going to get better and better at correcting errors. Okay. And it's not so important. I mean, obviously, having a higher threshold is better because you can get away with worse qubits. But having a threshold, I think, is one of the most important parts of a decoder or correction algorithm, because that means that there is a point at which you can stop worrying about your physical qubits. Here's the Torah game as an environment. You know, this is the state, just looking at where are the orange points and which of the dots, which of the bits have you already flipped. So these are the ones that you flipped, not the ones that I flipped. And the actions can just be performed, you know, on which you can pick each qubit and choose if you want to perform an X, Y, or Z operation on them. You can be a bit more clever. Let's not discuss that now. And the reward is just, you know, if there's still a syndrome, no reward. If you removed all of the orange dots and you have a contractible loop, you win. We discussed that, otherwise you lose. That's the whole name of the game. This you can look at in the, you know, in the slides that I sent you. That's the algorithm, and we've implemented all of that. This is something fun to look at also. The OpenAI Gym defines many environments for all kinds of problems, for the Atari games that we discussed, but also for these humanoids trying to learn to walk. And so, yeah, look at that. If you're not aware of it, there's also scigym.net, which is a collection of environments that are more tailored towards science rather than Atari games, for example. And I wanted to do another 5-minute break just to have a breather. So let me just show you very quickly the results of what happens if you take this Torah game and have a DeepQ agent learn to play this game. For two different settings that I didn't discuss. This setting on the left is when you have only X errors, only bit flip errors. And you see it's a little worse in some, so the dots, the symbols are the reinforcement learning agent, the others are the curves we just discussed before. It's a little worse. The threshold, I think, if you insist, is a little bit lower also than the minimum rate perfect matching, but overall it very closely follows minimum rate perfect matching. What's more interesting is if you go to the case where you have more than just bit flip errors, meaning you can also have Z or poly Y errors happening on physical qubits, then the reinforcement learning decoder learns to clearly do better than minimum rate perfect matching. And I think there's more to say for this also, because all of this assumed with minimum rate perfect matching that qubits are all identical, but in the lab they won't be. And a major advantage that I see, I think, with these learned approaches is that they will automatically learn that qubit number 17 is worse than qubit number 5, for example. Or if there's correlated noise sources, then it will also learn eventually, hopefully, that, you know, whenever qubit 4 flips, qubit 8 is also likely to flip, for example. So that's that. This I just wanted to flash very quickly because in real life, there's an extra source of errors, which is, you know, this is the one, if we go from left to right as a function of time here, this is the surface code, but forget it, you know, just look at the square, that's our Torah code from before. We can have errors happen. But there's another source of errors, which is from those ancilla qubits, right? Given that those errors happen, now we have to measure that syndrome, and that measurement itself can be faulty. So my measurement can say there is a syndrome when there's actually not, or vice versa. And so that gives you an extra source of errors, and that's the so-called fault-tolerant regime or faulty measurements regime. And you can even include that, and then the minimum weight perfect matching doesn't make sense anymore. And you can look at how long can I keep my code in a well-defined state. And if you do minimum weight perfect matching on in a time sliced version, let's not discuss that. You get some result. If you do that with a reinforcement learning agent again, you have 2 orders of magnitude in the lowest error rates, which luckily for us is also the regime where most actually qubits operate nowadays. Good. So that took a little bit longer than I thought, but that's because there were many discussion points in the beginning, and I prefer having discussion than me going over this. So that's a good thing. Let's take a 5-minute breather or so, and then I have another maybe 15 minutes of something I wanted to show before we end. And any questions are still, of course, welcome in the chat or here. Otherwise,
Question, I can.
Is it easy to see why the degeneracy of the ground state is 4-fold? And like, does it depend on the lattice size, or?
no, it does not. It's in.
You could put more than one non-contractible loops in there, no?
Yeah. It does not depend on the lattice size. It's a good question. I think if you don't mind, let's take that in the chat or offline, and then because that will take a little bit for me to go through. Then let everyone else go for a break, and then we can talk about that if you want, if that's okay with you.
Yeah, perfect. Thanks.
I think there's another question or not? Oh, sorry. No. Can you pass the mic?
If you want, we can wait after the break.
Go ahead. I mean, the previous question I think is a bit more involved for me to answer. So go ahead.
Yeah, so it's just, have you tried to implement a correlated noise or reinforcement learning scenario? Because it sounds very exciting to try and do it.
Yeah, short answer is no, actually. But there's a whole bunch of extensions and things that are going on, and this is one of them. And if you're interested, in that, reach out. I think there's definitely something that we can look at there still too.
Yeah, sure.
Sorry, one more question.
Yeah, of course. I'm happy that there's questions.
That's maybe slightly related, but it's going to be a very quick one. Do you know what's the stage with respect to reinforcement learning applied to design of quantum circuits? So like angle optimization of parameters and also design in quantum circuits, so the number of gates and so forth. Is there some work on that?
Yeah. Yeah, there's a bunch of different answers I can give to this. There's maybe the first one that I should reference that I can send in the chat is one from Austria, where they use so-called projective simulation, which is another very closely related to reinforcement learning. A very interesting technique by itself to learn about, where they use that technique, think of it as reinforcement learning, to design, for example, a full optical table. So now we're not talking about a quantum circuit, but the goal for the agent there was to place beam splitters and mirrors and so on a 2D grid, such that at the output you get a 3-qubit GHZ state, so a 000 plus a 111, for example. And that's very interesting. So that agent, you can see that it discovers all kinds of intermediate combinations of elements that you and I would recognize as, interferometer setups and so on. And at some point it designs that circuit and that optical circuit, and which, the students had not figured out how to do. So there you have a design of an example of designing an optical table in that sense as a circuit. There's also works on using reinforcement learning to design circuits, in particular to design, just a given unitary as a target. I have not seen any that really, that either some of them go for quite a few qubits, but they cheat because they give the agent access to the current unitary so that the agent can see the whole unitary, which, for many qubits is not going to be possible. The hard part, I think, here is scaling to more than a few qubits. I can send you some references where they do this for, 2 or 3 qubit circuit design, where you say either I start with all zeros and I want my agent to design a circuit to prepare a given target state. That's an interesting question that people are looking at. Yeah, so I'll get you those references. I can put them, I'll put them in the Discord.
Thank you.
Yep.
Okay, so let's take a 5-minute break and then we will finish the lecture.
Yep. Yep.
Hi, Evert. So we can even go a bit further. If you need a bit more time, we can do 5-10 more minutes more if you need.
Yeah, okay. That's good to know. I think I can go through the last part in a bit quicker. Most of the topics have been introduced. I'll try not to go over too far.
Okay, but if you need 5 more minutes, there is no problem. No, we will not stop.
Okay. Yeah. Thanks.
We have lunch and later for evening. So in fact, no more lectures
Yeah.
today. So okay to make
I
10
see.
minutes.
Oh, yeah, okay. But then good. Then you'll have a slightly colder lunch.
So we are all back and we can come back to the lecture of Evert.
Good. Okay. I was just typing away at Discord about the fourfold degeneracy question. Let's do that. I'll finish that later. Good. So we have about 10 minutes. Let's see how far I get.
No, 15.
So
15.
yeah. Okay. Okay. I'll, it's good. Tell me that I have 10 minutes and then we'll see how far I go over. We've seen reinforcement learning, in particular the DeepQ network quickly. We've now seen how we can formulate stabiliser or the Torah code or the surface code as a game in which we move the syndrome points. This evolutionary strategy is something that I think is fun to look at. It's a different way of solving, in this case, or playing that game. And it involves so-called policy networks. And the algorithm that I want to discuss is called the NEAT algorithm, stands for Neural Evolution of Augmented Topologies. And what that means, I'm going to explain shortly. So to do that, we need to take very one-slide introduction to genetic algorithms, and I realize there are whole courses about this. And so there's many variations that I can talk about here, but at the core, I think this is how I learned it and what I remember from it just off the top of my head. So in a genetic algorithm, we introduced the idea first of a population of many individuals. Okay, so I have some number of individuals, and for our purposes, each individual has assigned to it a number that I call the fitness. Okay, and that's an important number because I'm going to iterate the following process. Initially I generate many individuals and I give them a random fitness, for example, and then I'll have an example in a moment, more concrete, but then I iterate this. I take the top some percentage, let's say 20%, or that's a number, it's a hyperparameter that we can tune, the top fittest members of my population. And then I want to scale back my population to the initial size. So I take the first 20% and then I need to generate 80% more, but I want to do that in a way that increases the overall fitness of my population. Okay, so as long as the population size is smaller than n, this is a way of doing that. I pick a few, typically 2 of these individuals with a high fitness, and then I hope, I cross my fingers and say, I'll take some part of this individual and some part of the other. Hopefully the fitness of this individual is good because of one part and the other one is good because of the other, and I combine them. This is called crossover. In the jargon, you say you pick parent individuals and you generate offspring individuals, and you keep doing that until you are back to big population size. More concrete example of this in the next slide. So then I have a new population, and then each member also gets some random mutation, right? Some random genes or some random something that gets mutated. Can be different types of mutations with some probability p. I recalculate all of the fitness and I keep repeating this, and hopefully if I have the right so-called genetic operators, these 2 steps, then overall, as I keep doing and repeating this, like quote unquote evolution, the overall fitness of my population will go up. And of course, I would want that fitness to be tied to some problem that I want to solve, so that the higher the fitness, the better my solution. I remember in my course, when I learned this, the example was Sudoku. So let's do that here too. So imagine I have a population of, they can be solved, they can be unsolved. This can be used as a way to solve Sudokus. Let's think of it as a generator now. I have 1,000 solved or filled in Sudoku puzzles, maybe not necessarily solved. So here's 2 examples. And I have to define a fitness for my Sudoku puzzle. And one way of doing that is something that you have to play around with. is, for example, I can look at all the, I assume you all know Sudokus, so I'm not going to introduce them. I look at all the rows and columns and the blocks that are satisfied, meaning that numbers 1 through 9 appear in it once, and each of those gives me a +1. Or alternatively, I can, on top of that or instead of that, count how many times I violate one of those rules and then give a penalty. So I take 2 of those Sudokus in my population. I take the ones with the highest scores, highest fitness. And here's a way of doing a crossover. I take, 2 parents, and I take the top 5 of parent 1 and the bottom 4 rows of parent 2, and I cross them. So here, this new offspring has the first 5 rows of parent 1 and the last 4 of parent 2. And of course, I can also do the reverse. That's a crossover, and it turns out that for Sudoku, this will work. And then mutations are just, with some probability, I go over each of the squares, and with some small probability, I randomly change the number with or without checking the constraints. So it sounds like this is a random search, or if I just do this, it is just a random search. But this crossover is going to give you a direction in that search space. Very other well-known examples that I am not going to discuss is the CMA-ES algorithm. Maybe you've seen that for optimization. And one thing I can say here already is that this is an optimization technique for finding the highest fitness, and there's no gradients involved. I'm not taking gradients of any steps. So it's a gradient-free approach that we also heard about this morning from Bellman for a different setup. So now what we're going to try and do is, instead of Sudoku puzzles, I want to have neural networks. My individuals are now going to be neural networks, and their fitness is going to be determined by how well they play the game of solving quantum error correction. Right? Could be done by how well they play Flappy Bird, or how well they play Smash Brothers, or whatever favorite game you have. In this case, they're going to play the toric game. So NEAT does the following, which I'll explain in a second. It starts with simple neural networks with fixed number of inputs and fixed number of outputs. And then it starts to combine neural networks and mutate them, by adding or removing neurons. And so the way you do that in NEAT is by encoding networks. And I think this is a very clever idea. NEAT was not the first to do this, but I still think it's nice. By introducing a genome of a neural network. So we define, how many neurons it has and whether they're input neurons, hidden neurons, or output neurons. And then we have a sequence of genes, let's say, that I number with a unique number that says there's a connection from node 1 to node 3, that's this one, and it has value 1, and it's currently enabled. And there's also a connection from node 2 to node 4 with value -1.2, but it's currently disabled. You may ask, why do I disable instead of setting the weight to 0? Turns out that this is much more easy in our case if we just want to turn off or turn on neurons instead of changing the weights. So here's the genotype, and here's the phenotype that results from this set of genes. Was there a question? I thought I heard something. What? This genotype is going to be super useful in 2 slides when I start talking about crossover. But before that, this is the easier slide to talk about. This is the mutation slide. So this is how I would mutate the individuals. Namely, the mutations that NEAT allows are 2 node mutations where I add a node, which is simple to do in the genome. This is where the disabling comes in handy. So here I introduce a new node 4. So my connection from 2 to 3, which was here before I turn off, and I introduce 2 new ones, namely from 2 to 4, which is the new one, and from 4 to 3, which is here. And they get random weights. In the original NEAT, one of them kept unit weight. We decided in our implementation, they get random weights. So that's one mutation. That's how we augment the topology That's the augmented topologies. We grow the network. We can also remove nodes, by the way. And then there's weight mutations, which can, turn on or off weights like here, but they can also literally randomly change the weight of an existing connection, right, with some magnitude. And then there's crossover, which if I take two parents, so let's say I take these two individuals in my population, this one has this genotype and this one has that one. What I can simply do, because I'm keeping track of unique genes, I can align them based on these unique numbers. And then I can just, whenever they share a gene, I keep it and I pick, at random, I pick the weight between, parent 1 or parent 2. And that's also true if it's disabled. I randomly pick if I keep number 1 from parent 1 or number 1 from parent 2. If one parent has genes that the other one doesn't, I just keep them. And that's essentially it. Right? So that's aligning and keeping them. And this may seem simple. And now this is one of those cases where I've biased you, because now if I had given you these two networks just before and asked you combine these two networks into a third network in some meaningful way, it might not have been super obvious how to do that. There are different ways of doing that. This one is, I call this a meaningful crossover, or Neat calls that also meaningful, because in this case, with this network, we know that it's at least as good as either of the parents, because I could, in this case, just, turn off the new nodes that I have and I get back to either of these parents. So the networks that are in our population are going to not be Q networks like we had before, but in this case, maybe I should skip this, but they're just going to be policy networks. So for the Tic-Tac-Toe case or for the Torah Code case, they get in the state and they output, again, this bunch of numbers that we're not now going to interpret as Q values, but directly as the policy. This is a technical detail that in view of time, maybe I'll skip. So what it allows us, there's a few features. Some of them, it's gradient free. We can argue whether or not that's a good thing or not. But it is gradient free. So there's no neural network backpropagation in these networks. But the real advantage, I think, of NEAT, or the real thing that we wanted to see, what people claimed, is that it produces much smaller networks than Q-learning, still achieving the same performance. So because we start with the simplest network with only input neurons and output neurons, no hidden neurons, the hidden neurons have to come in through node mutations. You can show this more rigorously. I'm just saying it here hand-wavily. What will happen because of those node mutations and because of a mechanism called speciation that I can talk about in a moment, that complexity only grows when necessary. So if you find a small network that solves the problem well, it will have a very high fitness and it will survive every generation, and it will stay on top. And so you will very quickly filter out all the non-optimal solutions that have a lot of neurons. So that this speciation, just quickly mention it, is very important, because often when you add a neuron to a network that has a good fitness, meaning it can perform the game, play the game well, that mutation may completely kill its performance. And so you would immediately throw it out in the next generation. So instead of that, networks get grouped together by similarity, and there's a similarity measure here that that looks at, and again, that relies on the genes. You count how many they have in common, how many they have disjoint, and how many they have exactly matching. That gives you a way of saying these networks are similar, and you group networks that are similar. That's like introducing species. So that's why, even if you have within if you have a network because you mutated a very small fitness, if it's within another species, it has a chance of still surviving. I'm speeding up. I know I'm already 5 minutes over now. There's also straightforward transfer learning with these networks, if you know about them. And that's simply because once you have a trained network, let's say on this 3x3 lattice with these input neurons and the 4 output neurons, I can just take that network, use that as the new population, and all I have to do is add more input neurons with trivial connections, and then evolution can continue from there and start adding more hidden neurons as necessary. And you can clearly see that for larger code distances, if you look at, for a given error rate, this orange curve here, if you start from scratch, then the overall performance, in this case, how well does it correct the errors, goes up slowly. Whereas if you start with the d = 3, not even d = 5 initial network, it almost doesn't need to learn anymore. And of course you say, okay, that's not, the real question is, as you go to larger and larger codes, how much does this gap grow? And we can argue about that for a long time. My argument would be, why start down here if you can start up here and then train from there? Really, there's no loss that you hear. This is what the algorithm does. You can look at that yourself. This is the last thing I wanted to show. Here's a bunch of references that do reinforcement learning for error correction. I did not touch upon at all supervised learning or unsupervised learning for error correction. Those also exist. And so maybe in all fairness, this is a work that I was also involved in for different types of noise. And the networks, these were Q networks, used millions, 2 million or 9 million of parameters. And the neat networks we find for these cases use only a handful of parameters. These are parameters, are not neurons. So there's, in some cases, 4 orders of magnitude smaller networks that you get from this optimization technique versus Q learning. I don't know how small we could have gone with this number, for example, but at least, you already see if I wanted to go smaller here, I would have to try. I would have to see, okay, does a smaller network work? If I have the number of parameters, can I have it again? Does it still work? Whereas here, that's out of the question. You automatically find the smallest network that performs that task. And maybe I should just leave this up. The results are that network, of course, I wouldn't be showing this if it didn't work, basically learns to perform minimum weight perfect matching too. So it is a bit worse in some cases, and I think that can be fixed easily by doing some gradient updates. Remember, I think it's magic still, but the updates here of the weights are completely random, right? There's no gradient descent that moves the weights slightly in the right direction. And still you find networks that solve this task even better in high noise regimes, which we can also, I think, explain. Good. Here's the topics that we talked about. Feel free to ask me anything about these topics or other topics, either now or in the chat. But for now, I hope and I wish you a very pleasant afternoon and conference dinner. And I'll be around digitally if you have anything to ask. Thank you very much for your attention.
Thank you very much. Are there more questions about the last part of the talk or
So maybe I missed it, but what's your take-home message? You on one hand presented the reinforcement learning with deep Q learning, and now these evolutionary strategies. What are the ups and downs, or is there a clear better strategy for the things that you're proposing here?
Yeah, I think as far as I'm concerned, the Q learning, let me say, a reason for doing Q learning is that you have that Bellman equation that guarantees that if you optimize well enough, you get the optimal solution. For the evolutionary strategies, I cannot give you that guarantee. And that could be one reason why you would want to choose Q learning. I would argue, however, that we can tolerate some errors probably And so it doesn't have to be perfect and optimal. And in that case, we also want to think about minimizing energy consumption and so on. And there's lots of work going on in that direction. So the computational effort between these two is something that we would have to compare. The evolutionary strategy seems, better in that sense, but there's a whole lot of extra computations you have to do to evaluate the fitness. So okay, I'm now giving you a whole bunch of disconnected statements. I think my take-home message would be it would be nice to find smaller networks, period. And with no guarantees of how optimal they do, but we're also not after optimality. We're after, in this case, that algorithm having a threshold, which I flashed. It has a threshold, and that's what we care about.
Thanks.
Some more questions?
For problems in the deep queue network problem, for problems with a large configuration space, you encode the queue function into a neural network, right?
That's right. Yeah.
But when you can store all the configurations. So this looks a lot like neural network states. And so a question is, do people have a hard time sometimes encoding? If the policy is too complex, let's say they can't compress the information. I don't know if that was clear.
I'm not entirely sure what you were after. Can you try to rephrase it one more time?
So like the function you're trying to encode in a neural network with a smaller number of parameters, sometimes that'd be too hard to do, like in complex games such as Go, where they can't really do it.
Yeah, so exactly. You're right. So you're asking it now if there is an issue with how large my queue network has to be, for example, for my agent to learn anything, right? Maybe you're saying maybe it's not possible. Maybe my queue network has to be so large that it takes Google with all their TPUs to train it, and that's entirely correct. And so there are many tricks and many once you start doing deep queue learning that you will have to learn about. It's actually true that for it to be stable, you typically need two queue networks, one that you update every so often, because like I said, because for it to be stable. And what they do in AlphaGo, for example, they have a network that predicts that value function, not necessarily the queue function. And they use that value function to explore a game tree. This is Monte Carlo tree search. So it's slightly different from doing a pure reinforcement learning approach. And that value function is a bit more, a bit easier apparently to learn. But it's also very interesting because that value network, like I discussed, seems to capture that intuition that game players have, that they can look at a game and say this is a good state or a bad state. That's what the value does. And so that's where this AlphaGo in the end also got a lot of praise and attention about, is seeming to be able to capture that intuition rather than just brute force like Deep Blue, for example, minimax searches. So you do run into that issue of queue networks having to be so large or not learning, and then you need to find other tricks.
Thanks.
You're welcome.
Hi, thank you for the talk. My question is that maybe I missed the key reasoning, but I don't have the intuition as to why these evolutionary networks do so well in reducing the number of neurons. Especially when you explain the crossover process, it looks like the only way for it to drop a neuron was by mutation, but there's an equal chance of
Yeah. Sorry, I
Oh.
see the microphone stop.
Sorry, yeah, I was messing up the mic. So there's an equal chance of removing a neuron and increasing the number of neurons by 1, but you can also increase the number of neurons by merging during the crossover. So it seems
That's
that
right.
the evolution is biased towards even more neurons in each generation.
Yeah, you're entirely right. I think the essential point that you are skipping here is that in NEAT you start from trivial. So you start with the smallest networks possible. And you're right that you, on average, you can only grow. But at some point, for a given population size, you optimize everything. And because of these features that we can maybe, there's bonus content that I didn't discuss. I can really recommend, there's no citation that I can also add. I can really recommend looking at the original NEAT paper because it's quite nice to read. But the point is that you start from simplest, and with these mutation rules and this speciation mechanism that's down here, you clearly see that the complexity, meaning the number of nodes and your topologies of the individuals in your population, only grows when necessary, essentially, right? So sometimes you have a new network that has many more parameters, so it's much more complex than the rest. It belongs to one of the species. Maybe it's a species separate by itself because it's so different from all the rest. And if it's so different from all the rest, there's only one of them because it's much more complex. Most likely because it has a whole bunch of random weights. It doesn't perform very well. And that means in the next step, it immediately gets, thrown out because each species by itself is considered here. So if there's only one in a species and it has a low fidelity, most likely that species never survives. So it really encourages smaller changes. And if the complexity jumps immediately, most likely that doesn't survive. And that's a bit of intuition that I can give you. I hope that helps.
Yeah, thanks. Hi. So since we're talking about the complexity of the networks and how big they are, I was wondering whether there have been considered pruning techniques to simplify the networks resulting from the reinforcement learning algorithms, which I've mainly seen in the context of supervised learning, like performing classification tasks and so on. And they manage to reduce the networks by several orders of magnitude. And sometimes it turns out that they end up generalizing better and performing the task even better. So I was wondering whether this has been done in reinforcement learning or has even been considered here, like it would be more or less the opposite way in which you start from a big network and end up with a smaller one rather than starting from bottom to the top.
Excellent point. I think it hasn't been done simply because there's so many other things to do, but we could very well, like you're saying, actually, okay, I'm going the wrong way. There's a faster way this way. You say I could take one of these networks, and the comparison I'm making might not be is not entirely fair for the reason that these parameters, these are all Q networks. Now I can take those Q networks and, like you said, do a supervised approach where I take the same input to this Q network and I get out this the Q values. I can take the max of those Q values and use that as a target to train a policy network. I hope if I'm saying this, that makes sense. Most likely, like you're saying, that resulting network that just tries to mimic what this network is doing for the same input, tries to mimic what the same output is, hopefully, or based on this result, can be much, much smaller. I'm not sure if we're actually going to find it this small, but excellent suggestion. We haven't tried pruning these networks, but if you're up for it, I can send you the network. Okay, but thanks. That's an excellent suggestion. Yeah.
So thank you, Evert. And I think for today we are finished, and I think Michał wants a comment.
Yes, so thank you, Evert. I think now the comments is for people on site. So, so thank you. Maybe we can once more. Thanks for the great lecture. Yes, so I know you are hungry, but give me like 3 minutes. So first of all, we have today the school dinner. So Anya sent you the link on Discord. It's Kameralna restaurant Kameralna. It's in the historic center. You can, and we meet at the dinner starts at 7:30, right? And you can go there by bus from here, or it's from the center, from the hotel. It's relatively easy. And then I have maybe just used a suggestion, because of course today you have free afternoon. Then there is free Sunday, and next Wednesday is free. So of course you can use this time for discussing machine learning, what I recommend, but you can also use this time for discussing machine learning and sightseeing Warsaw. So maybe I just give you some hints what interesting things can be found. So it will take just 3 minutes. So of course we have like Old Town. The Old Town is on the UNESCO list, but it's something specific because it's on the UNESCO list, not because of its historic value, but because of its value of reconstruction. Because of course, as all Warsaw, it was fully destroyed during the war. So to the Old Town, it's like half an hour by bus, for example, 175 from here. Then there is Old Town, which is from like originating from Middle Ages. There is Royal Castle. So if someone like sightseeing castles, it's very nice